In this video, we're going to look at Lab 3.1 on digital circuit operation. So the purpose of this lab is to begin examining the DC and AC behavior of basic gates. And so we want to actually start putting down parts onto our breadboard and providing power to them, power and ground, and looking at their outputs as we drive them with different input patterns. So what we're going to do is we are going to power our breadboard in this lab using the Analog Discovery supply output, and we're going to provide plus 3.4 volts to our breadboard, and then we'll use them to power our basic gates. And then we're going to look at the DC operation of our gates using a logic analyzer while we drive logic inputs into it using the arbitrary waveform generator. And then we'll do that for an inverter, an AND gate, and an OR gate. And then what we'll do is we'll hook up the oscilloscope to the inverter, and we'll take a look at the analog characteristics of the input and output, and we'll take some measurements on the transition time and propagation delay, and we'll actually look at what happens when the input signal is not within specification. Okay, so whenever you use a new part, one of the first things you need to do is look at its data sheet. So the first thing we want to do is look at a data sheet and determine the pinout and the input and the output, and I'll bring up the data sheet over there. The input and the output specifications, both DC and AC, and then what we want to do is learn how to use the Analog Discovery, look at logic analyzer measurements, oscilloscope measurements, etc. So what you're going to want to do is get your breadboard and wires out, your Analog Discovery, and you're actually going to go into your parts kit now and look at the HC04 inverter, the HC08 2-input AND gate, and the HC32 2-input OR gate. So let us begin. There are a series of deliverables that we'll walk through in this video. But the first thing we want to do is take a look at the data sheet. So if I pull open the data sheet for the inverter, the nice thing about logic gates that are in the same family is you only have to look at the you can get an idea for how they operate by just looking at one of the parts in the family, because they're all going to have about the same characteristics. But when you pull open the 74 HC01 datasheet, the first thing you notice is that it gives you a couple different pinouts for different packages. We are going to be using the DIP, or dual inline package, which looks like this, and you'll see right here what the inputs are and what the outputs are. So the inputs are A and the outputs Y. Now remember, this is actually 6 inputs on here. Okay, and then what we're going to do is, so that's how we're going to wire it up. We want to take a look at the characteristics now. So let's go down here. You've got your recommended operating conditions, input high, input low. These are kind of interesting. So the high level input and the low level input. You know, in an ideal situation for CMOS, the ideal input and output, or excuse me, input high, input low are going to be VCC and ground. And the ideal output are going to be VCC and ground. So what we're really interested in is looking at what's the minimum input that'll actually make this thing work, and what's the minimum output that we would ever get. So recall that we're in the 74HC series, and they don't give you the numbers for the power supply that we're using. What they do is they give it for a power supply at 2 volts, 4.5 volts, and 6 volts. And 6 is the highest you can drive power it with, 2 is the lowest. And then what you have to do is you have to kind of interpolate what the values would be. And so if you refer to chapter 3 in the textbook, you'll have, there's an interpolation example. But you can kind of see that we're going to be powering ours with 3.4. So the high level input minimum is going to be somewhere in between 1.5 and 3.15. And so you can kind of like draw a little chart out and you can figure out what that value is. And then for the low, what you're going to do is it's going to be somewhere, the highest that the logic low could be is somewhere in between 1.35 and 0.5. So the first thing you want to do is kind of draw out a little interpolation graph and kind of just take a stab at what those numbers are. And then for the output, the same thing. When you look at the VOH, you're going to have a similar thing. So under, you know, if you look over here, we'll use this 20 microamp situation. The output high in the worst case is going to be somewhere between 1.9 and 4.5. So obviously not going to be over 4.4. So it's it's gonna be somewhere around 2-ish, 2.1, and then for VOL, the highest it would ever be is it's stuck basically at 0.1. Another thing we are interested in is how fast this thing would switch. Okay, so switching characteristics, propagation delay is TPD, and if you come over here, you notice that if you power it with 6 volts, the slowest it would ever be, max, is 20 nanoseconds for the time that it transitions. 24 if you power of 4.5 volts, and then it goes way slower at 120 nanoseconds if you go to 2 volts. And the reason that this gets so big is because it's reaching the point where it's not operating anymore. So if you think about this, basically if you powered at 3.4, you're going to be somewhere around like 20, let's say 28, because it was 20, 24, and then 28 for a 3.4 volt supply. And same thing when you go to transition time. 6 volt power supply, you're going to be at transitioning at 16, 4.5 you're going to be at 19, but then at 2 volts where it's almost not working anymore, it gets really slow and goes to 95. So you're going to be somewhere near the 19, so probably 23 or 24. Okay, so the first thing you want to do is grab those values out of there so that we know kind of what we're looking at. And then let's go ahead and start breadboarding up the 3 basic gates. So what I do in this handout is I give you the schematic that we're going to use, and I show you the actual drawing of how they're pinned out. So when we take a measurement, we don't want to just hook up the inverter and leave its output dangling. We want to have a load. So a load is what you call whatever you're driving. So this is what we'll do is we'll have a load that's another basic gate, and this is really easy to do because all of these parts have other gates in them that aren't being used. So all we're going to do is we're going to use this first inverter right here, for example, and we'll just take its output and let's just connect it to the input of the next inverter. That way it's not just free floating, it actually has a load, but it's not going to have much of an impact. So that's just a little technique we like to do so that the output isn't dangling. Same thing for the AND gate, same thing for the OR gate. And what I do is I kind of show you an example of how to put this on your board, but let's take a look at my board here. And what you'll see on your parts kit is you're going to have these, these gates, and as you take them out of the if you take them out of the package, the first thing that you notice is that these things are kind of angled outward and they don't go directly into your breadboard. So what you have to do is you have to kind of take them and you have to pinch these, just very gently pinch these leads so that they're kind of more straight in. And then what you do is you can always tell pin 1 by the little divot inside of there. And these breadboards are actually designed to accept these parts straddling this center line. Okay, so I didn't get my pins enough. Okay, and so they're made to kind of go just like that. So what I recommend you do is put your inverter, AND gate, and OR gate in just like this, boom, boom, boom. And I still don't have my leads enough on there. Okay. And then I want to give you one more piece of advice to avoid. Okay, so there we go. When you go to take these out, do this. Okay, either use a needle nose plier or a pen, and what you do is you slide in like this, and you can just pop them right out. Don't do this. Okay, this will save you a lot of pain. Don't come in here and pinch these and try to pull them out, because when you pinch them, it's really hard to grab them, and what happens is you pinch harder and harder and harder. At some point that thing will pop out, and you almost always will squeeze into these leads, and those leads will go into your finger and you'll start bleeding. Okay, so never try to take one of these parts out using your fingers. Always use some other tool like a needle nose plier or just a pen or a pencil, and you just put it in this little gap and you just pop it out like that. Okay, so that's an important lesson that I learned the hard way. So you put these babies in there and you need power. Okay, so the power comes from this pin right here, pin 14, in the upper right hand corner. And what you're going to do is, if you remember, we set up our breadboard so that the red is connected throughout the breadboard. So what we can do is we'll bring the power into the entire breadboard using the red supply channel from the analog discovery, and then we'll bring the ground in from the analog discovery, and I just use 2 little pins and stuck them in the red strip and the blue strip of my breadboard, and that provides it throughout the entire breadboard. Then I can just take a little jumper wire and go from the red over here on this strip into that strip, and I've got power now over there. And then I can do the same for the AND gate and the OR gate. And then to get ground, I simply use another wire and come down here to pin 7 on each of these devices, and I jumper that over into the ground strip. These little red wires are how I connect the output of the gate to the input of the next gate down, so you can just use those little guys. And then what I want to do is I'm going to drive the inverter first using the arbitrary waveform generator. So I bring the arbitrary waveform generator in over here, and I just have the little pins, and I put it right there on pin 1, which is the input. And then I'm going to use a logic analyzer to measure the input and the output. So I use channel 0 right here to measure the input, and I use channel 1 to measure the output. So that's what your breadboard will look like. And now all we need to do is turn on the power and take a measurement. So you bring up waveforms, and the first thing that we got to do here is turn the power on. So there's a new tool we're going to use this time called supplies. And when you do supplies, it's got two power supplies, V plus and V minus. We don't want to use V minus. We can provide a negative voltage, but we're not going to do that. So if you click on that, it'll turn it off, and then when you run the power supply tool, this one won't produce a voltage. So go ahead and turn that off first. For this guy right here, we want to set that. We're going to power everything with 3.4, so I just do that. And then what I do is if I want to power my board, I just hit run, and what happens is that then turns on the power supply to my board. Okay, and you can see that it's the master enable is on right now. Okay, so now what we're going to do is we will begin taking a measurement of the inverter. So what I want to do is I've got power to my board, and I want to drive in a logic signal and then observe it. So I'm going to go back to my welcome, and I'm going to turn on the wave gen. So if you remember the wave gen tool, what we want to do is we are going to make this a square wave, and let's run it fast in this lab. Let's run it at a kilohertz. So leave the frequency at that. The amplitude is going to be 1.7, which means it's going to swing above 1.7 and below 1.7 around an offset, which we'll put at 1.7. And by setting those two like that, I get a signal that swings from 0 up to 3.4. Okay, so I go ahead and run now the waveform generator, and now I have what I have is I'm driving in an input signal into pin 1 of the inverter, and so I can actually look and see if this is working. So the way that I'm going to look and see if it's working is I'm going to look at the logic analyzer tool. So let's go back to the welcome, and let's go to logic, and what I'm going to do is I'm going to add the input and the output as logic channels, and remember that I have channel 0 on the input and channel 1 on the output. So I'm going to hit this plus, and this time I'm going to hit signal, which means just a single signal, and I'll go ahead and hit DIO0, and then I'll add another signal, and I'll say it's DIO1, and now I'm ready to take a logic analyzer measurement. So I can actually double click on this, and just to keep it kind of consistent, let's name this A, just to make it match our drawing, and then we'll call the output F. And what I'm going to do is I'm going to hit run on here, and notice there it is. So I got my logic analyzer measurement going, and it's banging around because I don't have my trigger set. So I hit stop, and you can see on here that it's working as I anticipated. It is an inverter. So look at the input. It is nothing more than a logic 0, logic 1, logic 0, logic 1. But the output now is a logic 0 and a logic 1 also. So we did it. We actually built a circuit of an inverter by using this part right here, and we drove in a logic 1 and a logic 0, and we were able to measure the output as a logic level, and we did it. So this inverter, what's cool about this is that it didn't work without power, so we had to provide power and ground to it. So that was the first step. So then we learned how to use the new tool of the analog discovery, and we just verified it. So for what we're going to do first is you're going to take a screenshot of this for your records, and that demonstrates the operation of the inverter. The next thing you want to do is make sure that you can do the same thing for the AND gate. So now for the AND gate, what you're going to do is you will hook up, you can only do this one at a time, each gate, because you need the arbitrary waveform channels to drive the inputs. So since there's only two arbitrary waveform channels, when you go to the AND gate, you need two inputs, A and B. So you're going to move your arbitrary waveform channels onto the AND gate and drive in a 2-bit binary counter and then observe the output. Remember, to configure the arbitrary waveform generator to do a 2-input binary counter, you can refer back to lab 2. 2.1. So when you do the AND gate, what you should see, you're going to need 3 logic analyzer channels, 0, 1, and 2, and go ahead and label them A and B and F. And then what you'll see is on the output, F only ever goes high when you have both A and B high. And so take that measurement, take a screenshot, and you've verified that the AND gate works. And then you'll do the exact same thing for the OR gate. Okay, and notice the OR gate will be high for anytime the inputs either A or B are high, and so take a screenshot of that. And what you've done at that point is you have verified the operation of all 3 of these basic gates. Now we're ready to start looking at the analog behavior of the inverter, and we do this with an oscilloscope. So the next section, what we want to do is we want to disconnect the logic analyzer, and we'll hook up the oscilloscope to the inverter. So we're just going to look at the analog behavior of the inverter because it kind of represents all the other gates and in terms of how they transition. So if you go back to your breadboard, what you're going to want to do is disconnect the logic analyzer channels, and so I'm going to take those over here, and I just leave my jumper wires or pins in the same position because we're going to measure the input and the output using the 2 channels of the oscilloscope. So now on the oscilloscope, what you're going to want to do is grab 1 plus and 2 plus, which are the oscilloscope channels, and let's put channel 1 on the input to the inverter. We'll put channel 2 on the output of the inverter. And then remember with the oscilloscope, the oscilloscope channels have their own reference, which we always tie to ground for these measurements that we do. And so we want to make sure that these are connected to the ground of the breadboard. So what I'm going to do is I put these little pins into there, or you can use the jumper wires, and then I'm going to put these into the ground of the breadboard. So I'll just pop those into the blue rail right there, and now I've configured my oscilloscope measurement. Okay, so now let's go back into waveforms, and now what I want to do is I want to bring up the oscilloscope tool. So I'm going to go back to welcome and hit scope, and that's going to launch the oscilloscope tool. And so when that comes up, there's a couple things we want to do. First, let's set up the trigger, and then we'll just hit run and see what comes on the screen. So the first thing that we want to do is, my background's white right here. Just remember, if you ever want to change the background of that, you just hit this little gear button, and you can change it to light, and then you can thicken up your plot widths. So the trigger, we want to have t equals 0 represent right when the input transition or the output transitions right in the middle. So as it goes from 0 to 3.4, right in the middle of that, we want that to be our trigger, and then all the data will be graphed to the left and the right of that. So what we want to do is come up here, and mode is auto, and then let's do the source for the triggers, channel 1, conditions rising, and then for level, go ahead and type in 1.7. Okay, when we do that, we should be able to hit run, and you'll see the oscilloscope running. Okay, and so you get these waveforms on here, and this is great. So you can kind of see what's happening as I zoom in and out here. But what would be neat is to be able to see this a little bit clearer. So to do that, here's what you can do. Let's go ahead and come over to here, and for the range on channel 1, let's do 1 volt per division, and then for channel 2, let's do 1 volt per division, and that makes them so we can see them on the screen. You can also drag them up and down vertically by coming over here to these little triangles. These triangles represent the reference voltage, and in our situation it's 0. So if I click on here, you can drag these up and down, and notice that when I click on them, the scale over here turns to the color of the channel. So notice that when I clicked on this, 0 now is the blue, and that's that level. Then when I click on this, 0 is down here. But if I do this, I now have, and then for time, you can kind of go to like, I don't know, 0.5. Let's see, for my screen, I had about 0.2 milliseconds. So go ahead and do like 0.2 milliseconds, and then put the position back at 0, and there you have it. So you now have a analog measurement of the inverter, and it looks very similar to the logic analyzer because we're zoomed way out, but you can see that the input comes along and it goes up, and then the output is already up and it goes down, and it's an inverter. So this is great. This is just a analog view of it, even though we're zoomed way out. So go ahead and take a screenshot of this for your records, and this will satisfy the deliverable for the exercise that says I'm looking at the analog behavior of that. Okay, so now, and that's deliverable number 3. Now what we want to do is we want to take a look at the impact of a signal that doesn't meet the minimum input specifications. So if you recall what input specifications are, this right here is the input, okay? And we know that it has to go down a certain level at a certain voltage to be considered a low, and it has to be at least high enough or large enough to be considered a logic high. But it has a range of values that it can actually take on and still work. So what I can do is I'm going to look at starting to shrink this input signal and see when the output basically stops working. So to do that, I'm going to go in, I'm going to modify the wave gen. So I'm going to go back into wave gen, and over here, since I can't see it very well, I'm going to change that to light and crank that up to 4. And so what I'm going to do is let's just leave the offset at 1.7 and then let's shrink the amplitude. So if I go in and I shrink the amplitude to 1 volt, and then I go back to the oscilloscope, look at what happened here. Oh, I'm sorry. This is the input down here. So let's put the output on the bottom and the input on the top. And notice now, since they're on the same scale, these are representative of what they actually look like relative to each other. This is actually getting pretty small. But notice that the output is still working very well. So it means that the input can actually shrink quite a bit before the output starts messing up. If I go into WaveGen, I can also shrink this more. I can also pop this out. So if I wanted to have this be a separate window somewhere, I could pop this out so that it's easier to control. So I'll go ahead and shrink it way down and kind of put it over here. And then let's go ahead and shrink it down to like 0.5. Now look at that. It's still working though. It's crazy. The input can be tiny, so 0.4. It's like, okay, it's still working, 0.3. And oh, look at what happened. When we shrunk down to 0.3, the output stopped doing exactly what it was supposed to be doing. All of a sudden, it wasn't going all the way up to a high. It was like, only went up to like half of the way up. And so it's like, okay, we're starting to see the first signs of this freaking out on us. So and even notice it's kind of jumping around. So somewhere in here, like if I make it a little bit bigger, look at this output behavior. It's going nuts. So it's nuts because it's not getting a big enough input signal in order to operate properly. So it doesn't really know whether the input is a 0 or a 1. So this is the impact of not meeting the input specifications of the gate. The gate cannot determine what it's supposed to do because the input doesn't meet its specs. The way to think about it is it's the input sitting in a region where the gate doesn't know whether it's a high or a low, so it's just its output can't make a good decision. So this is actually the deliverable for number 4. So put it right where it's freaking out and go ahead and take a screenshot of that for your records, and that will be the deliverable for number 4. And then finally what we want to do is let's look at the AC characteristics of the inverter, and by that I mean let's take a look at what its transition time and rise time is. So in order to do that, we want to look at actually the transition from a high to a low on the input and the output. So I'm going to go back to my wave gen and I'm going to put 1.7 on the input. So now we're back to a regular input swing, and I want to put these right on top of each other because I'm going to zoom in on the transition. So let me put these on top of each other. Let's crank the zoom on these both to 0.5 so we can really zoom in. So I'll drag that down there and I'll drag that down there. And now what I want to do is I want to zoom in. So I can zoom in over here on the time base. Let's go ahead and go way in. So I don't know, you can go down to like 0.1 microseconds and look at how far we zoomed in there. Let's go to, not that. Let's go all the way to, let's see, what did I say in the handout just to be consistent? We're down to like 0.05 microseconds. Okay, so 0.05 microseconds. And this is now zoomed way in on the input and the output. And what we care about is this transition when we talk about the specs. So I want to measure the propagation delay. And remember, the propagation delay is defined at the point where the input crosses the 50% mark, so going from 0 to 3.4, that would be right at 1.7, and the time it takes for then the output to transition to the 50% mark. The way that I can do measurements in the analog discovery is to hit this button right here called Hot Track, and what it does is it gives me a cursor, and I can come along and drag it, and it'll show me information. What I really care about here is I put it roughly on the 1.7 volt mark, and I noticed that X is at negative 600 picoseconds. So that's negative because it's to the left of the 0 mark. So that's 1 point in time. And then I come over to here to the 50% mark, and it's at 9 nanoseconds positive. So basically, the delta between these two, if I calculate it out in my head, it's 9.6 nanoseconds. And it's like, okay, well, that's reasonable relative to what we thought. It's a lot faster than what we originally did, but we just now measure the propagation delay. The rise time, or transition time, is the point at which the output goes from its 10% to its 90%. So 10% would be somewhere around, 0.34 volts, so somewhere right in this region. And if I look at the time here, you got negative 10 nanoseconds when it starts moving, or excuse me, on the output here. So about right here is like, let's say it's at 0 seconds, so that's kind of handy. And then we'll go all the way down here to about right here, and that's 13.9 nanoseconds. So I can measure that and say, the transition time is about 14 nanoseconds. And so that's faster than what we thought, but it all depends on the load that you have. So I just now measured the transition time. And that's the end of the AC characteristics. So take a screenshot of this window. HotTrax doesn't automatically give you those deltas. You have to kind of like write them down and subtract in your head. Just remember that if it's a negative time, that just means it's to the left of the trigger. And so take a screenshot of that with HotTrax on, zoomed in to this level so you can see the input and the output. And that's the last deliverable for this lab. So you've done it. So if you think about this lab, ask yourself if you can do the following. Can you look at the data sheet and determine the pinout and the DC and AC specifications for a logic gate? And do you have the ability now to use the power supply output of the analog waveform generator? And can you use that to verify the logic operation of a basic gate by driving in an input using the arbitrary waveform generator and observing the output using a logic analyzer? Can you also measure the AC or the analog behavior of a basic gate with an oscilloscope? Can you describe in words the impact of an input signal that doesn't meet the minimum input specification of a gate and how that impacts the output? And then finally, can you use an oscilloscope and zoom in on the transitions and measure the propagation delay and the transition time of a logic gate? If you can do that, you have successfully completed this lab, and we are done.